Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The quest to understand the fundamental nature of matter has always been a pursuit fraught with both theoretical ambition and experimental ingenuity. In the mid-20th century, this endeavor reached a critical juncture, demanding verification of a profound theoretical prediction of the existence of antimatter. At the heart of this challenge stood Owen Chamberlain, a physicist whose meticulous experimental work would fundamentally alter our comprehension of the universe. The central problem that propelled Chamberlain and his collaborators was to confirm the existence of the antiproton, a particle with the same mass as a proton, but with an opposite electrical charge. This seemingly simple task, however, demanded a sophisticated approach to overcome the inherent difficulties of detecting a particle predicted by theory but never before observed. The theoretical foundation for the search rested firmly on the work of Paul Dirac. Dirac's relativistic quantum mechanics, developed in the late 1920s, had not only successfully described the behavior of electrons, but had also, rather unexpectedly, predicted the existence of antimatter. His equations, when applied to the electron, suggested the possibility of a particle with the same mass but an opposite charge, the positron. The positron, subsequently discovered by Carl Anderson in 1932, provided the first tangible evidence supporting Dirac's radical concept every particle should have a corresponding antiparticle. This theoretical framework, so elegantly formulated, implied a symmetry in the universe. For every particle of matter, there should exist an antiparticle of antimatter. The implications of this symmetry were staggering, as it suggested a deeper, more fundamental structure to reality than previously imagined. The prediction of the antiproton, the antimatter counterpart to the proton, followed naturally from Dirac's framework. The proton, the nucleus of the hydrogen atom, was known to be a stable particle. Its antimatter equivalent, the antiproton, should therefore also exist. The challenge, however, lay in the experimental verification. The antiproton, if it existed, would be incredibly difficult to find. It would be produced in high-energy collisions, and its detection would require discriminating it from a plethora of other particles, many of which would share similar characteristics. The experimental task was akin to searching for a single specific grain of sand on a vast, windswept beach. The intellectual impetus for Chamberlain's work, therefore, stemmed directly from Dirac's theoretical predictions. Dirac's equations, the cornerstone of relativistic quantum mechanics, provided the theoretical basis and the driving force for the experimental search. Dirac's work, in essence, gave the researchers a target. The work of Emilio Segrè, a colleague of Chamberlain, also played a crucial role. Segrè's earlier work on the discovery of the antineutron, the neutral antiparticle of the neutron, provided valuable insights into the behavior of antimatter and the challenges of its detection. Segrè's experimental expertise and his understanding of particle physics were instrumental in shaping the experimental approach. Segrè and Chamberlain's collaboration proved to be a powerful combination of theoretical insight and experimental skill. The search for the antiproton demanded a powerful tool, a particle accelerator, capable of producing the high-energy collisions necessary for its creation. The Lawrence Radiation Laboratory at the University of California, Berkeley, provided precisely that. The Bevatron, a proton synchrotron, was specifically designed to accelerate protons to energies exceeding 6 billion electron volts, GeV. This energy level was crucial. It was estimated that the antiproton, with a mass nearly equal to that of the proton, would require a significant amount of energy to be created in a collision. The Bevatron, therefore, was the instrument of choice, providing the energetic particles needed to probe the fundamental structure of matter. The experimental strategy, the specific methodology Chamberlain and his team devised, was predicated on a series of carefully designed steps. The Bevatron would accelerate protons, which would then be directed toward a target, often a copper block. The collisions between the accelerated protons and the target nuclei would produce a wide range of particles, including, hopefully, antiprotons. The challenge then became one of sifting through this complex particle soup to identify the relatively rare antiprotons. The solution involved a sophisticated system of particle detection and analysis. The experimental setup included a magnetic spectrometer, a crucial component for selecting particles with the correct momentum. The spectrometer, a device that utilized a strong magnetic field, would bend the paths of charged particles. The radius of curvature of a particle's path in the magnetic field is directly related to its momentum. By carefully measuring the curvature, the experimenters could select particles with the momentum expected for antiprotons. Following the magnetic spectrometer, the particles would pass through a series of detectors. These detectors were primarily scintillation counters, devices that emit light when struck by a charged particle. The light emitted by the scintillators would be detected by photomultiplier tubes, which would amplify the faint signals. The timing of the signals from these counters would be critical. By measuring the time it took for a particle to travel a known distance, the experimenters could determine its velocity. This time of flight measurement, combined with a momentum measurement from the magnetic spectrometer, enabled them to identify the antiprotons. The data analysis was equally complex. The signals from the detectors were processed using sophisticated electronics. The experimenters employed coincidence circuitry, which only registered a hit when multiple detectors registered a signal within a specific time window. This helped to filter out background noise and to isolate the events of interest. The experimenters also used pulse height analysis, which measured the intensity of the signals from the scintillators. This provided additional information about the energy deposited by the particles. The culmination of this meticulous work was the publication of the seminal paper in * Physical Review * in 1955. This paper, co-authored by Chamberlain, Segrè, Clyde Wiegand, and Thomas H. Lennes, announced the discovery of the antiproton. The paper provided a detailed description of the experimental setup, the data analysis techniques, and the conclusions drawn from the results. The team reported the unambiguous identification of antiprotons, particles with the same mass as protons, but with a negative charge. The evidence was compelling. The data demonstrated that antiprotons were being produced in the high-energy collisions at the Bevatron, and that they behaved exactly as predicted by theory. The discovery of the antiproton was a triumph of experimental physics, confirming Dirac's theoretical vision and opening a new chapter in the exploration of the fundamental building blocks of the universe. The discoveries impact extended far beyond the immediate excitement of the scientific community. The confirmation of antimatter's existence revolutionized particle physics. It provided crucial validation for the standard model, the prevailing theory describing the fundamental particles and forces of nature. Chamberlain's and Segré's work paved the way for the discovery of other antiparticles, including the antineutron, and provided the foundation for advancements in our understanding of the universe's fundamental symmetries. The techniques and methodologies developed in this experiment, especially those related to particle detection and time-of-flight measurements, continue to be used in modern particle physics experiments, such as those conducted at the Large Hadron Collider at CERN. The magnetic spectrometer, a key component of the experiment, remains a fundamental tool in particle physics research. The discovery of the antiproton, therefore, stands as a testament to the power of experimental physics, a demonstration of how careful observation and ingenious experimental design can unveil the deepest secrets of the cosmos and influence generations of physicists. The experimental design, a testament to ingenuity and precision, was meticulously crafted to achieve a singular goal: the definitive identification of the antiproton. The challenge was formidable. The Bevatron, the particle accelerator at the heart of the endeavor, was designed to generate high-energy protons. These protons, colliding with the target, would, according to theoretical predictions, produce a cascade of secondary particles, including the elusive antiproton. However, the antiproton, if it existed, would be a rare guest in this high-energy party, easily masked by a deluge of other particles with similar properties. The apparatus, therefore, needed to be a sophisticated filter, a selective sift capable of isolating the antiprotons from this chaotic melange. The core of the experiment revolved around a magnetic spectrometer. This instrument, a cornerstone of particle physics, exploited the fundamental principle that charged particles moving through a magnetic field experience a force. The magnitude and direction of this force depend on the particle's charge, velocity, and momentum, as well as the strength and configuration of the magnetic field. By carefully shaping the magnetic field, the spectrometer could selectively deflect particles based on their momentum. This was achieved through a series of carefully positioned magnets arranged to bend the trajectories of the particles. The curvature of a particle's path within the magnetic field provided a precise measurement of its momentum, allowing the experimenters to select particles within a specific momentum range. The precise momentum selection was, of course, only the first step. The next challenge was to distinguish between particles with the same momentum, but different masses. This is where the concept of time of flight became critical. The time of flight technique leverages the relationship between a particle's velocity, the distance it travels, and the time it takes to traverse the distance. If the distance is known and the time is precisely measured, then the velocity can be calculated. Knowing both the momentum and the velocity, the mass of the particle can be determined. This is because, for a given momentum, a heavier particle will move slower than a lighter one. To implement this, the experiment employed a series of scintillation counters. These devices, which were state-of-the-art at the time, were exquisitely sensitive. They worked on the principle of fluorescence. When a charged particle passed through the scintillator material, it would excite the atoms, causing them to emit a flash of light. These light flashes, or scintillations, were then detected by photomultiplier tubes, which amplified the faint signals into measurable electrical pulses. The experimental setup included two sets of scintillation counters, strategically positioned along the path of the particles, separated by known distance. The first set of counters, placed before the magnetic spectrometer, served as a trigger, initiating the measurement process. The second set, positioned after the spectrometer, was used to detect the particles that had been selected by the magnetic field. By accurately measuring the time it took for a particle to travel between these two sets of counters, the experimenters could determine its time of flight. This, combined with the momentum measurement from the spectrometer, provided the necessary information to calculate the particle's mass. The experiment further incorporated coincidence circuitry, a powerful technique for filtering out unwanted background events. The coincidence circuit was designed to register an event only when both a signal from the first set of scintillation counters asterisk and asterisk a signal from the second set of counters were detected within a specific time window. This ensured that only particles that had traversed the entire experimental apparatus were recorded, significantly reducing the background noise. The width of this time window was precisely tuned to account for the expected time of flight of the antiprotons, while excluding particles that arrived at significantly different times. Additionally, the experiment employed pulse height analysis. The intensity of the light produced by a scintillation counter is, to a degree, proportional to the energy deposited by the charged particle passing through it. By analyzing the height of the electrical pulses generated by the photomultiplier tubes, the experimenters could gain additional information about the nature of the detected particles. This proved useful in further discriminating against background events, as different types of particles would deposit different amounts of energy in the scintillator material. The design and construction of the experimental apparatus were a testament to the ingenuity of the researchers and the technological capabilities of the time. The Bevatron, a marvel of engineering in its own right, provided the high-energy proton beam. The magnetic spectrometer, with its precisely calibrated magnets, performed the crucial momentum selection. The scintillation counters, with their rapid response times and high sensitivity, provided the means for time-of-flight measurements. The coincidence circuitry and pulse height analysis acted as sophisticated filters, carefully sifting through the background noise to reveal the faint signal of the antiprotons. The specific configuration of the experimental components, the precise alignment of the magnets, and the careful calibration of the detectors were all critical to the success of the experiment. The researchers meticulously documented every aspect of the experimental setup in their publications, providing detailed schematics and descriptions of the apparatus. The calibration procedures, which ensure the accuracy of the measurements, were also carefully described, allowing other scientists to reproduce and verify the results. The impact of this experimental design extends far beyond the specific discovery of the antiproton. The techniques and principles employed, such as particle detection, time-of-flight measurements, and the use of magnetic spectrometers, have become fundamental tools in particle physics research. These methods are still in use today, refined and improved in experiments at facilities like the Large Hadron Collider at CERN. The development of the magnetic spectrometer, in particular, has had a lasting impact on the field. It is a versatile instrument used to measure the momentum and charge of charged particles in a wide range of experiments. The design of the Bevatron itself for example, influenced the design of other particle accelerators that were constructed in the years following the antiproton discovery. The success of the experiment also inspired other researchers to pursue similar investigations, leading to the discovery of other antiparticles, such as the antineutron. The experimental techniques and methodologies pioneered by Chamberlain and Segrè provided a foundation for future advancements in particle physics. The experimental work of other physicists working at the time also provided direct influences. The methods used in particle detection and the experimental setups of researchers studying the properties of the neutron, for example, likely influenced the design of the antiproton experiment. The use of scintillation counters and coincidence techniques were already established in the field, and the researchers adapted and refined these methods for their specific needs. Having established the experimental framework and the methods for particle detection, the focus shifted to the crucial stage of data analysis and the extraction of definitive results. This phase demanded meticulous attention to detail, sophisticated statistical techniques, and a rigorous assessment of uncertainties. The challenge was formidable to discern the faint signature of antiprotons from the overwhelming background of other, more common particles generated by the Bevatron. The core of the analysis involved a multifaceted approach, beginning with a careful examination of the events recorded by the detectors. The team, guided by the principles of experimental physics and the theoretical predictions of Dirac, employed a series of sophisticated techniques. One critical element was a precise measurement of the momentum and velocity of the detected particles. The Bevatron's magnetic field, through its influence on the trajectories of charged particles, provided a means to determine their momentum. Simultaneously, the time-of-flight measurements, derived from the timing signals of the scintillation counters, yielded information about the particles' velocities. These two parameters, momentum and velocity, provided a powerful means of identifying the antiprotons, which were expected to have the same mass as protons but with an opposite electric charge. The data analysis process was far from straightforward. The detectors registered a vast number of events, many originating from interactions other than the desired antiproton production. These background events, created by the collision of protons with the target material, produced a complex array of secondary particles, including pions, kaons, and other particles with similar properties to antiprotons. To isolate the antiproton signal, the researchers employed a series of carefully designed cuts and filters. These were criteria applied to the data to eliminate events that did not meet the expected characteristics of an antiproton. For instance, events with a momentum or velocity outside a specific range were discarded, as these were unlikely to be caused by antiprotons. The team also carefully considered the expected flight path of the antiprotons, using the detector's spatial resolution to eliminate events that strayed from the predicted trajectory. The statistical analysis of the data was a cornerstone of the effort. The researchers, drawing upon established statistical methods, constructed histograms and plots to visualize the distribution of the measured quantities. These plots served as crucial tools for identifying the antiproton signal. For example, the team plotted the number of events as a function of the time of flight, creating a distribution that revealed a peak corresponding to the expected arrival time of antiprotons. The width of this peak, which reflected the uncertainty in the time of flight measurements, was carefully evaluated. The team also plotted the momentum of the particles, again looking for a distinct peak that would correspond to the expected momentum of the antiprotons. The application of these statistical techniques allowed the researchers to extract the signal of the antiprotons from the background noise. The team needed to determine the mass of the antiproton. The mass, a fundamental property of the particle, could be calculated from a measured momentum and velocity. The team meticulously employed relativistic kinematic equations, the same equations used to determine the mass of other particles, to calculate the mass of each candidate antiproton. The individual mass values were then combined to obtain an average mass for the antiproton, along with an estimate of the statistical uncertainty. The uncertainty, a crucial aspect of any scientific measurement, was carefully quantified. This involved identifying the sources of error, such as the resolution of the detectors, the precision of the time of flight measurements, and the uncertainties in the magnetic field strength. The researchers then used statistical methods to propagate these uncertainties through the calculations, resulting in a final value for the antiproton mass accompanied by precisely defined error margin. The results of this thorough analysis were presented in a seminal paper published in the Physical Review. The paper presented compelling evidence for the existence of the antiproton. The data revealed a clear peak in the momentum distribution corresponding to the expected momentum of the antiprotons. The time of flight measurements confirmed that the particles detected had the correct velocity to be antiprotons. The calculated mass of the antiproton was found to be consistent with the mass of the proton within the experimental uncertainties. This crucial finding, the agreement between the antiproton mass and the proton mass, provided strong support for Dirac's theory of antimatter and the underlying symmetry between matter and antimatter. The statistical techniques employed in this groundbreaking experiment were not developed in isolation. The researchers likely drew inspiration from the statistical methods used in other areas of experimental physics at the time. For example, the analysis of data from nuclear physics experiments, which often involved the detection of particles and the measurement of their properties, had already established a set of powerful statistical tools. These tools, including the use of histograms, the calculation of mean values and standard deviations, and the application of error analysis, provided a framework for the antiproton experiment. The researchers adapted and refined these existing methods to meet the specific challenges of their experiment, developing a comprehensive approach to data analysis that would set a standard for future experimental work in particle physics. The influence of these statistical methods extended beyond the immediate context of the antiproton experiment. The techniques used to analyze the data, including the careful consideration of experimental uncertainties and the use of statistical tests to evaluate the significance of the results, had a profound impact on the development of experimental physics. The rigorous approach to data analysis, emphasizing the importance of statistical rigor and the quantification of uncertainties, became a hallmark of the field. The success of the antiproton experiment hinged on the meticulous application of these statistical techniques. The team's ability to extract a weak signal from a noisy background, to accurately determine the momentum and velocity of the detected particles, and to carefully assess the associated uncertainties, ultimately led to the unambiguous identification of the antiproton. This validated Dirac's theoretical predictions and opened a new chapter in particle physics, confirming the existence of antimatter and paving the way for further exploration of the fundamental building blocks of the universe. The methods used, refined from the existing landscape of experimental physics, provided a framework for future advancements in particle physics. The experiment and the resulting data analysis represented a triumph of experimental skill and theoretical understanding. The discovery of the antiproton resonated far beyond the immediate confines of the Bevatron and the laboratory. It provided a critical validation of the Dirac equation, a cornerstone of relativistic quantum mechanics, which, from its inception, had predicted the existence of antimatter. The Dirac equation, formulated by Paul Dirac in 1928, had elegantly unified quantum mechanics with special relativity, predicting the existence of particles with the same mass as their matter counterparts, but with opposite charge. The antiproton, the negatively charged counterpart of the proton, was the first such particle to be experimentally confirmed. This confirmation was a pivotal moment, directly impacting the understanding of fundamental physical laws. The implications of the antiproton's discovery extended to the CPT theorem, a fundamental principle in quantum field theory. The CPT theorem, which stands for charge conjugation, parity inversion, and time reversal, posits that the laws of physics are invariant under the combined transformations of these three fundamental symmetries. Charge conjugation involves swapping particles with their antiparticles. Parity inversion reflects space through the origin, and time reversal reverses the direction of time. The experimental properties of the antiproton, specifically its mass and charge, provided strong evidence for the validity of the CPT theorem. The antiproton's mass, meticulously measured and found to be identical to that of the proton, and its charge, meticulously measured and found to be equal in magnitude, but opposite in sign, offered robust support for this fundamental symmetry. These confirmations helped to establish the framework for the standard model of particle physics. The immediate impact of the antiproton discovery extended to the burgeoning field of cosmology. The symmetry between matter and antimatter, as demonstrated by the existence of the antiproton, raised profound questions about the early universe. The Big Bang theory, the prevailing cosmological model at the time, suggested that the early universe was a state of extremely high energy and density, where matter and antimatter should have been created in equal amounts. If this were the case, the universe should have quickly annihilated itself, leaving only radiation. The fact that the universe exists and is overwhelmingly composed of matter presented a significant puzzle. The antiproton discovery, while confirming the existence of antimatter, simultaneously highlighted the asymmetry between matter and antimatter. This discrepancy forms the basis for ongoing research in cosmology, as scientists seek to understand the mechanisms that led to the observed matter-antimatter asymmetry. The discovery of the antiproton spurred a wave of further investigations. The confirmation of the antiproton's existence motivated the search for other antiparticles, including the antineutron, which was subsequently discovered. This, in turn, fueled the development of experimental techniques and theoretical frameworks within particle physics. The ability to create, detect, and analyze antiparticles became an essential component of the field. The antiproton experiment served as a model for future experiments, demonstrating the importance of careful experimental design, meticulous data analysis, and rigorous statistical methods. The techniques developed by Chamberlain, Segrè, and their team were adopted and refined by subsequent generations of physicists, enabling further discoveries in particle physics. The antiproton discovery also had a significant impact on the development of particle accelerators and detectors. The Bevatron, the accelerator used in the experiment, was a monumental achievement of engineering. The successful operation of the Bevatron and the subsequent detection of the antiproton demonstrated the feasibility of creating and studying high-energy particles. This, in turn, led to the construction of even more powerful accelerators, pushing the boundaries of experimental physics. The detectors used in the antiproton experiment, such as the scintillation counters and the Cherenkov detectors, were also refined and improved. These advancements in accelerator and detector technology were crucial for the progress of particle physics. The work of Dirac, a theoretical physicist, profoundly influenced the direction of the experimental endeavor. His prediction of antimatter provided the theoretical foundation for the experiment. His mathematical framework, embodied in the Dirac equation, provided the theoretical underpinning that both motivated and guided the experimental search. The experimental confirmation of Dirac's theory provided a powerful validation of his approach to theoretical physics, solidifying his place as one of the most influential physicists of the 20th century. The experimental work of Wolfgang Pauli on the exclusion principle also played a crucial role, albeit indirectly. The exclusion principle, which states that no two identical fermions can occupy the same quantum state simultaneously, is fundamental to understanding the behavior of matter. The discovery of the antiproton and the subsequent confirmation of its properties reinforced the validity of the exclusion principle, which is a core tenet of the standard model. The understanding of the exclusion principle, a fundamental tenet of quantum mechanics, was crucial for interpreting the data from the antiproton experiment. The discovery of the antiproton directly influenced numerous subsequent investigations. The confirmation of the antiproton's existence spurred the search for other antiparticles, including the antineutron. This, in turn, fueled the development of experimental techniques and theoretical frameworks within particle physics. The ability to create, detect, and analyze antiparticles became an essential component of the field, influencing the design and execution of future experiments. The antiproton experiment served as a model for future experiments, demonstrating the importance of careful experimental design, meticulous data analysis, and rigorous statistical methods. These developments were crucial for the advancement of the field. The discovery of the antiproton was not merely an isolated event. It was a pivotal moment in the history of physics. It validated a theoretical prediction, confirmed a fundamental symmetry, and opened up a new era of exploration. The experiment, with its meticulous approach, rigorous methodology, and insightful analysis, continues to serve as a model for scientific investigation. The legacy of the antiproton discovery continues to shape the field of particle physics and our understanding of the universe. The meticulous application of statistical techniques, refined from the existing landscape of experimental physics, provided a framework for future advancements in particle physics. The experiment and the resulting data analysis were a triumph of experimental skill and theoretical understanding. The confirmation of the antiproton's existence, spearheaded by Owen Chamberlain, resonated far beyond the confines of the Bevatron. It represented a confluence of theoretical prediction and experimental validation, a testament to the power of scientific inquiry. Paul Dirac's earlier theoretical framework, which posited the existence of antimatter, provided the crucial foundation. The implications of this work were profound, extending into cosmology and the very foundations of our understanding of the universe. The discovery offered a tangible demonstration of the symmetry inherent in physical laws, a principle that continues to guide physicists in their quest to understand the fundamental building blocks of reality. The experimental design itself offered a masterclass in scientific precision. The team's approach, which built upon the expertise of Emilio Segrè, involved a series of sophisticated steps. The Bevatron, a particle accelerator capable of generating the necessary high-energy beams, served as the primary tool. The experimental setup involved a complex array of detectors, including scintillation counters and Cherenkov counters, all meticulously calibrated and synchronized. These instruments were designed to identify and measure the properties of the particles produced in the collisions, discerning the fleeting signals of the antiprotons from the background noise. The challenge was formidable: to isolate a particle with a mass equivalent to a proton, but with an opposite charge. The data analysis presented its own set of hurdles. The team, drawing upon the established methods of statistical analysis, meticulously sifted through vast amounts of data, searching for subtle signals that would confirm the antiproton's existence. The application of the appropriate statistical techniques, which were a product of the broader advancements in experimental physics, became critical. This process, which involved careful consideration of potential sources of error and the employment of rigorous statistical methods, allowed the team to confidently assert the discovery. The team's success hinged on their capacity to distinguish between genuine signals and random fluctuations, an ability that demonstrated the importance of careful experimental design and rigorous data analysis. The antiproton discovery, as a consequence, served as a catalyst for further exploration. It provided a powerful model for subsequent experiments in particle physics. The techniques developed by Chamberlain and his colleagues, including the use of sophisticated detectors and the meticulous application of statistical methods, became standard practice in the field. These methods would later be adapted and refined by researchers across various disciplines. The legacy of this work extends to the present day, shaping the way physicists approach experimental design, data analysis, and the interpretation of results. The impact of the antiproton discovery extended beyond the immediate scientific community. It captured the public imagination, highlighting the power of scientific inquiry and the potential for groundbreaking discoveries. The story of the antiproton, with its elements of theoretical prediction, experimental ingenuity, and meticulous analysis, became a compelling narrative. It also underscored the importance of international collaboration as the research drew upon the expertise and resources of scientists from around the globe. The discovery also had profound implications for cosmology. It helped to refine our understanding of the early universe. The existence of antimatter, as demonstrated by the antiproton, raised fundamental questions about the origin of the universe and the imbalance between matter and antimatter. This imbalance, which remains one of the great mysteries of modern cosmology, sparked further investigations. The discovery of the antiproton, therefore, became a cornerstone of modern cosmology, providing a crucial piece of the puzzle in our quest to understand the universe's origins and evolution. The theoretical and experimental frameworks that Chamberlain and his colleagues developed continue to shape our understanding of the cosmos. The significance of Chamberlain's work is further illuminated by the fact that it was directly influenced by the theoretical framework of Dirac. Dirac's work, which predicted the existence of antimatter, provided the crucial theoretical foundation for the experiment. The knowledge of Dirac's work was a critical element in the team's success. The experimental confirmation of Dirac's prediction through the discovery of the antiproton was a validation of a theoretical framework. This interplay between theory and experiment is a hallmark of scientific progress, and the antiproton discovery provided a prime example of this dynamic. The discovery also had a direct impact on subsequent generations of physicists. Chamberlain's work, along with the contributions of his colleagues, directly influenced the development of new experimental techniques and theoretical models. The work served as an inspiration for countless researchers. The meticulous approach to data analysis and the rigorous application of statistical methods, for example, became a standard for particle physics research. This legacy extends into the present day, with researchers continuing to build upon the foundations laid by Chamberlain and his team. The discovery of the antiproton, therefore, serves as a testament to the power of scientific collaboration and the enduring impact of groundbreaking discoveries. The experimental techniques developed by Chamberlain and his team, which were refined from the broader landscape of experimental physics, continue to be relevant in modern particle physics experiments. The use of scintillation counters, Cherenkov counters, and other sophisticated detectors, which were pioneered in the antiproton experiment, are still employed in modern particle accelerators. The principles of data analysis and the rigorous application of statistical methods, which were central to the antiproton discovery, remain essential in the interpretation of experimental results. The legacy of Chamberlain's work continues to shape the field of particle physics. The discovery of the antiproton also served as a powerful demonstration of the importance of collaboration. The experiment involved a team of researchers from diverse backgrounds, each bringing their unique expertise to the project. This collaborative spirit, which was a hallmark of the scientific community at the time, played a crucial role in the success of the experiment. The collaboration fostered a dynamic exchange of ideas and a shared commitment to scientific excellence. The legacy of this collaborative approach continues to shape the field of particle physics, with researchers from around the world working together to unravel the mysteries of the universe. The antiproton discovery, in essence, was a pivotal moment in the history of physics. It validated a theoretical prediction, confirmed a fundamental symmetry, and opened up a new era of exploration. The experiment, with its meticulous approach, rigorous methodology, and insightful analysis, continues to serve as a model for scientific investigation. The legacy of the antiproton discovery continues to shape the field of particle physics and our understanding of the universe.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.